wrapping up solutions and solubility by discussing acids and bases. So a little bit of theory based on acids and bases. And we know that we've got, there's a fear about acids and bases when it comes to the lab. And of course, there are acids everywhere, even in the foods, right? So here, let's look at a few common acids and bases that we actually have in the household, right? We've got the citrus acid or citric acid that's found in fruits, okay? Ascorbic acid we've got in dairy, right? Lactic acid in vinegar, acetic acid, carbonic acid here in soft drinks, underarm odor sprays or the sticks, okay? We've got acids. In terms of bases, right, we've got oven cleaners, baking soda, glass cleaners, right? So we've got these things, and of course, we always want to make sure that when we handle some things that, of course, like an oven cleaner, right? You want to make sure that you're using the appropriate, safety gloves, right? The rubber gloves that are usually associated to cleaning. Now, let's look at acids, okay? So just kind of recapping, right? If you think about anything, foods, drinks, right? Lemon juice, right? Acidic, tastes sour. Okay, they change color when we use an indicator, right? So for those who remember the litmus paper test, right? Red, right? We think of the D for acid, not really the best one, right? But think of for the next one. So red will stay red if it's an acid, but also blue litmus paper will turn red in an acid. Okay, so you can use red or blue litmus paper. Now for bases, they taste bitter, slippery feel. Okay, there's also a color change when using indicators. Now, here's the thing, right? If you're using blue litmus paper, it will stay blue, right? So we think of blue for base. But now, if we were to put red litmus paper in, that red litmus paper will turn blue if it's a base. Other indicators, right? We've used phenolphthalein in the lab. If the pH level, okay, the pH is between 0 and 8.2, so we're going from acidic to slightly basic, right? Phenolphthalein will stay colorless. Anything beyond that, right? So when we, so anything that's greater than, let's say, a pH of 8.2, right? We see that fuchsia color. Remember that pinkish color that we saw in the lab? So usually it's with something that's basic. And so when we were looking at the one that we did in our lab, remember that when it turned pink, right? We used sodium hydroxide. So we used sodium hydroxide. Sodium hydroxide is a strong base. So obviously it was going to change into that pinkish or that fuchsia color. So most bases will turn that color. Acids will actually remain colorless. Another property that can be used to distinguish acids from bases is their conductivity in solution. So if we were to hook up a power source here and we've got our little light source, right? Because there are ions that are formed in solution, right? The dissociation. Remember when we looked at how something like HCl can dissociate into the following ions, right? So these ions can help carry that charge, right? That can cause the light source to light up. Right? So aqueous solutions of acids and bases conduct electricity, right? So this is proof that ions are present in acidic and basic solutions. So if you had something that was acidic, something that was basic, you would be able to have the light shining. Of course, if you use something that was neutral, right, like water, there aren't really any ions that are forming, right? So you're not going to get the light to shine, right? And of course, the brighter the light shines, the more concentrated the ions are. right? Because remember, the more ions that are present in the solution will allow for a brighter, right? If the light, that was shining wasn't as bright, it was dim, right? Then you knew that the concentration of the ions wasn't as strong. Some observable properties of acids and bases. So if we look at acids and bases, their taste, so we know is sour, one's bitter. Electrical conductivity, well, they both conduct electricity. In terms of feel, right, of course, we would never really want to touch, right, any acids that we're unaware of. Of course, you can touch your, soda pop or vinegar might spill on your fingers. But if something was considered acidic, there's really no feeling to it. Right? It just kind of feel like a regular liquid. But anything that is basic or alkaline feels very slippery. Now, some other properties. In terms of reaction with litmus paper, right? Remember what we talked about? Red for acids, blue for bases, right? So, it turns blue litmus paper to red, right? Remember what we said? So if we were putting blue, even though blue is for basic, right? If we're putting blue into an acid, we're changing that blue to red, right? Or if we're keeping it red, it'll stay red. But for bases, it'll turn the red litmus paper blue. But if we put blue litmus paper in it, it'll stay blue. Okay. Reaction with active metals produces hydrogen gas, right, for acids. And for bases, do not react when we're mixing with. So think about in your acid-base reactions, right? In most acids, as we said, start with the hydrogen. Most bases contain the hydroxide. If we're combining a metal, right, with the base that contains the hydroxide, right, we're just going to displace the other metal. So there's really no real reaction that will actually occur because you're still keeping that basic solution. All you're doing is just creating a different type of base. Okay, and we're going to talk about the OH. Remember how we said hydrogens are the hint for acids, hydroxides are the hint for bases, but there are some exceptions to the rule, and we're going to see that today. Reaction with carbonate compounds, right? Acids will produce carbon dioxide gas, while bases will not react. The Arrhenius theory of acids and bases. The pattern of acids and bases dissociating was first noticed in the late 19th century by the Swedish chemist named Svante Arrhenius. Now, we talk about dissociation, and that's where we dissociate an actual compound. So it will break apart into its respective ions, right? Into its respective positive and negative ions. So we have hydrogen, or with the chlorine, so hydrochloric acid, that will dissociate into its hydrogen ions and chloride ions. The sodium hydroxide will dissociate into its sodium ions, right, Na+, and the hydroxide ions. Right? So what we've already known up until now was, well, to determine if something was acidic or basic, we looked at the concentration of the hydrogen ion, and we've looked at the concentration of the hydroxide ion. So everything that we've done up until now with acids and bases, like back in grade 10, right? We've looked at the Arrhenius theory. That's what we've used. That these acids and bases dissociate into their respective ions, right? Either hydrogen ions or hydroxide ions for bases. Acids dissociate in water as follows. So we've got hydrobromic acid will dissociate into what? The hydrogen, right? Hydrogen ion. And the bromide ions, right? The sulfuric acid here will dissociate, right? It'll dissociate once. So if we remove one hydrogen, we're still left with HSO4 aqueous, right? But because we've removed the hydrogen, it carries a negative charge. In fact, and we're going to see this in the next chapter, what happens is this can actually further dissociate. Sulfuric acid is a strong acid once it dissociates this way. The minute this dissociates this last hydrogen, that version of the ion is actually considered a weak acid. Last one here, the chloric acid will dissociate, actually the perchloric acid will dissociate hydrogen and the perchlorate. So, notice how we're removing the hydrogen. The hydrogen dissociates, right? So all of them contain hydrogen. So all of them are acids, right? Now, these bottom ones in terms of bases, right? And again, they're in water. How do we know they're in water? Aqueous, the AQ. Right? So they're in water. But notice, what's the one thing that's missing in all these equations? The water, right? Where's the water? We're going to see that in a second. So, when lithium hydroxide breaks apart into, right, the lithium, right, AQ, plus the hydroxide, AQ. Potassium hydroxide into the K plus, and the OH, right, again, OH, right, as we've known, bases, OH. The last one, barium hydroxide. This one's a little bit trickier because we've got this subscript 2, right? It's one barium, right? But what's the charge on barium? It's a plus 2, right? It's a plus 2 aqueous. Right? It's in group 2 of the periodic table. Right? And the hydroxide, right? We've got hydroxide, right? But how many do we have? 2 of them. So we put 2 in front. So that's just the balancing, right? That's how we balance it, right? So, notice how bases dissociate. All bases. Got the hydroxide. All our acids here have the hydrogen ion. Now, in 1887, Arrhenius published a theory to explain the nature of acids and bases. It was called the Arrhenius Theory of Acids and Bases. And they go as follows. An acid is a substance that dissociates in water to produce one or more hydrogen ions. Right? So that dissociation that we just did, where the H plus was removed, and then we had whatever non-metal, right? The non-metal anion. Right? And bases, similarly, but it wasn't that the H was dissociated, it was the OH that became dissociated. So, according to his theory and what we've done in terms of acids and bases, the OH meant that we had a base. The hydrogen dissociating meant we had an acid. Problems. Right? So we've got here hydrochloric acid dissociating into its H plus ions and the chlorine ions. Okay, and according to Arrhenius, he said, well, this is what's going to happen. We knew that the concentration of these hydrogen ions is what's going to determine pretty much, if something was an acid or a base. But remember how we said, where's the water? If it's dissociating in water, right, where's the water in this equation, right? So we know that whenever anything dissociates, it's in the presence of water, right? It's an aqueous solution. So we should include water into our equation, right? So here's the following. We're going to include the water, right? But notice water really doesn't change. Right? It's still, the water still remains as water. It's just kind of, it dissociates. But the thing is ever look at a hydrogen? So let's look at, oh my goodness. Let's look at hydrogen, right? The H plus, right? So draw a simplified Bohr-Rutherford or Bohr diagram of the H plus ion, right? So we've got the nucleus, right? This is simplified. So this is elementary. This is grade 9 way of drawing atoms, right? So we've got our nucleus, and inside the nucleus, we've got what? Protons and neutrons. What's circling? Electrons. But if it's H plus, Do we have any electrons? No. We just have a nucleus. So H plus is nothing more than just one proton, because hydrogen has one proton. The atomic number is 1. What's the number of neutrons? 0. So all H plus is a proton. Okay. So that's really where the question is. And what we're going to also see is protons really don't remain in pretty much these type of aqueous solutions as is, right? So they're not gonna circle around. So chemists in the early 20th century realized that protons do not exist in isolation in aqueous solutions. So they can't dissociate that way. So where do they go? Right? That's really what we're going to be looking at right now. The hydrogen ion, as we said, just a proton. It is positively charged nuclear particle. No neutrons, no electrons. Just that one proton, that's it. Right? So what happens to that? Well, what happens is it actually jumps on board with the water. So instead, protons are always considered hydrated. They are attached to water molecules. So here we have our one proton here, hydrogen. Here's the molecule water. So it's going to combine itself with the H2O to form this compound called the hydronium ion, H3O positive 1. Because why is it positive 1? Because we've just added a proton. Right? We've just added that extra. So all of a sudden now this formula, right, that whole dissociation doesn't really work. Right? So now we're going to not ignore it, because we do want to be able to distinguish between the two methods, and we're going to see the more appropriate way of drawing it. So a hydrated proton is called a hydronium ion, H3O plus, and it's an aqueous solution, so it's in water. Now, another problem with the Arrhenius method: dissociate the following base. NH3 ammonia is a base. So if it dissociated, right, for it to be a base, what did we say a base is contained? OH. There's no OH. Right? But somehow, right, with the way it reacts with water, we'll be able to create that, and we'll see that. So here is the real reaction. We've got ammonia combined with water, right, in the presence of water, aqueous. Right? Notice now the subscript here, L, right, liquid, combines, and what happens is the water is going to give up one of the hydrogens. Right? And what is the NH4 positive 1? The ammonium ion, right, that we've seen back in the polyatomic chapter. And then here's our base, the OH, negative. Right? So it doesn't look that way based on the dissociation method that was brought up by Arrhenius. So it didn't work here with some of them. Here then we had the following two chemists worked independently from one another. But they came across this theory called the Bronsted-Lowry theory of acids and bases. And they came in to explain where the problems lied with the Arrhenius method that now would work with all acids and bases. So, an acid is a substance from which a proton, the H plus ion, can be removed. So we can take away a hydrogen proton and put it somewhere else. Give it to one of the other molecules. Right? A base is a substance that can remove a proton from an acid. So one's going to either give the proton, one's going to pretty much receive the proton. And so that's really where the real acid, real bases lie. But again, that's still the idea of the OH, right, for our bases is there. Now it's no longer the hydrogen positive, right, the hydrogen ion, it's actually the hydronium ion. According to the Bronsted-Lowry theory, there is only one requirement for an acid-base reaction. One substance must provide a proton, and another substance must receive that same proton. So one of them is going to give up the hydrogen proton. The other one must pick that up. Right? So the one that picks it up, right, is what's going to become the acid. The one that gives it up is what's going to be the base. So technically, anything can act like an acid, anything can act like a base. So an acid-base reaction involves the transfer of a proton. That's the key point here with the Bronsted-Lowry. And you need to be able to identify it. Right? You had a reaction, you had a dissociation method. Can you tell from that, if it was either Arrhenius or Bronsted-Lowry? So, according to their theory, any substance can behave as an acid, but only if another substance behaves as a base at the same time. Right? So anything can be an acid, anything can be a base as long as they behave that way. Which means one's going to give up a proton, the other one's going to pick up that proton. If they don't do that, then of course it's not acting as the acid-base pair. So any substance can behave as a base, again, but only if the other substance behaves as an acid at the same time. So it's that vice versa method. So here we have hydrochloric acid and water. Obviously we know which one is the acid. The hydrochloric acid, right? So we know this has got to be the acid. Which means water has to act as a base. Right? So water's got to act as the base. Which means only one of them, it has to give up the proton, the hydrogen proton, to the other. And the other one's going to pick it up. Right? And we know that what's going to happen is the following. Which gave it up? The acid, right? The acid gave up that proton to the so-called base. Right? So that H donated the proton to the water. Right? The water picked up the hydrogen proton to form the hydronium ion. That's what we're determining as the concentration for the acid. Right? Which means if that's the acid, the other's got to be the base. And so what we have is, we have the following terms. Okay? Two molecules or ions that are related by the transfer of protons are called conjugate acid-base pairs. Right? So what we have, conjugate meaning they're linked together. So what we have here, we have something called a conjugate base. So a new term that we need to know. Of an acid is a particle which remains when a proton is removed from the acid. A conjugate acid of a base is a particle that results when the base receives the proton from the acid. So we know that the HCl was our acid. We know that the water is going to act as a base. Okay? And in return, we've just formed the following acid. Right? The hydronium ion. And the hydronium ion is considered the conjugate acid because it has picked up. It has picked up the proton, and which gave up, right? The HCl or the Cl now that's on its own is considered the conjugate base because it was the one that actually gave up the proton. Right? So if we look at this, the conjugate base of an acid is the particle that remains when the proton is removed. So the proton was removed from HCl, and that's what's left. So that's what makes it the conjugate base. The conjugate acid, as we said, is the one that actually receives the proton. The water received the proton. So because it received the proton, it's considered the conjugate acid. According to the Bronsted-Lowry theory, every acid has a conjugate base. Every base has a conjugate acid. Okay, so what we have is here, this equation, no different than what we've had or what we just looked at. Okay? So this acid is going to give up the hydrogen. The one that picks up the hydrogen now becomes the conjugate acid. Well, the one that gave it up has become the conjugate base. So it's really important that you do understand these concepts. Conjugate base and conjugate acid of an acid-base pair are linked by the transfer of protons. So remember, the proton got transferred from the HCl to the water. The water picked up, right, that hydrogen ion, thus becoming the H3O. Because it picked it up, it's considered the conjugate acid. Because this one gave up that hydrogen here, it's known as the conjugate base. Now, the conjugate base of the acid-base pair has one less hydrogen than the acid. It also has one more negative charge than the acid. So the conjugate acid of an acid-base pair has one more hydrogen than the base. It also has one less negative charge than the base. So what we have here, notice now, we've got the positive charge and negative charge. Right? So the positive charge associated with the conjugate acid, the negative charge with the conjugate base. Let's look at a sample problem. Here's the following sample problem. Hydrogen bromide is a gas at room temperature. It is soluble in water. Okay, so when we dissolve it in water, it becomes hydrobromic acid. So identify the conjugate acid-base pair. So here we're starting off with the reactants. Okay, so figure out now what the products will be, and then figure out and then label which ones are your acids, which ones are your base, which one becomes your conjugate acid, which one becomes your conjugate base. Which one of these is the acid? Or that's going to act as the acid? HBr, right? The hydrobromic, right? Hydrobromic acid. The water is what's going to act as the base. So which one's going to give up the proton? The hydrobromic, right? It's going to give up the H to the water to form the hydronium ion, right? So this is what ensues in the end. So we know that, here we've got the hydrobromic acid, right? This is the acid. The water here is going to act as a base. It's not a base, but it's going to act as a base. Now, which one of these is the conjugate acid? In our products, which one of them is the hydronium ion, right? So this is going to be the conjugate acid, which means the Br negative is the conjugate base. So if we're looking at something called the conjugate acid-base pair, we're always looking at it as the acid has a conjugate base. All right, so we take acid and think of it as this way. Acid with the conjugate, the linked with base. Right? So this is what we call the conjugate acid-base pair. So the hydrobromic acid with the bromide ion are considered the conjugate acid-base pair. These two are conjugate acid-base pairs to one another. So they are also another conjugate, right? Conjugate acid to base, conjugate base to acid, or whatever you kind of want to name it. But it's always, if you have an acid, you've got to have its complementary, which is its conjugate base. Last sample problem. Ammonia is a pungent gas at room temperature. Its main use is in the production of fertilizers and explosives. It is very soluble in water. It forms a basic solution that is used in common products such as glass cleaners. Identify the conjugate acid-base pairs in the reaction between aqueous ammonia and water. So take a moment and actually come up with their conjugate acids and the conjugate bases. Which one of these two is going to act as the acid? The water. Which means the ammonia is the one that's going to act as the base. So which one of these two is going to give up the hydrogen proton? The water is going to give up the hydrogen to the ammonia. Right? To form NH4, right? The ammonium ion and the hydroxide ion. So which one is the conjugate acid? The ammonium, right? And the hydroxide is the conjugate base. So you want to look for, right, the conjugate base is easy to find if you got OH in your ending. Right? The conjugate acid is easy to find if you've got the hydronium ion. Do we have the hydronium ion? No, we have the hydroxide ion. So that's why it makes things a little bit easier. But another way to tell is which one of them gave up the proton, which one picked up the proton. So if it picked up the proton, it's the conjugate acid. If it gave up the proton, it's the conjugate base. So which ones are the conjugate acid-base pairs? Ammonium with ammonium, with the ammonia, right? The base with the acid, but it's the conjugate. And which means that the water is a conjugate acid-base pair with the OH. So notice the pairing. Acid with a conjugate base. A base with a conjugate acid. Those are the pairs. Let's compare. Let's wrap it up by comparing both theories. So according to Arrhenius, an acid, any substance that dissociates to form hydrogen ions in an aqueous solution, right? The H+, that's what we've known up until now. But as of today, we've kind of been introduced to the Bronsted-Lowry, which pretty much caused anything that gave up, right? So anything that donates a proton to another substance, right? That's what an acid is. So which one is going to give up the proton? Bases, right? Anything that dissociates to form the hydroxide ion. Yes, we're still forming the hydroxide ion with the Brønsted-Lowry theory, but this is the actual substance that actually receives the proton. So the one that receives the proton is considered the base, or should we say, ultimately forming a conjugate base. So, example for both of them: hydrochloric acid dissociating into H+ ions and chloride ions. But the difference here with the Bronsted-Lowry is that we're actually including water into this equation. Which means, with the Bronsted-Lowry, which one of these two is going to give up the proton? The one that gives up the proton, the one that donates a proton, is the acid. Which means if the other one picks up the proton, it has to pick up the proton, is the base, which will ultimately form, right, the conjugate acid and the conjugate base. Please don't do the short form like I did right here on a test or quiz.